Hello everyone, this is Varun. Welcome to Aerospace Structures. Today we are going to discuss about the aircraft loads. The maximum loads on the component of an aircraft structure generally occur when aircraft is undergoing some form of acceleration or deceleration. When you consider an aircraft, it may accelerate or deaccelerate. As a result, a form of force is applied on an aircraft. The type of loads acting on an aircraft is classified as landing and takeoff loads, inertia loads, and manual loads. These are the three type of loads which are acting on an aircraft. The landing loads are acting when an aircraft touchdowns at a certain point on the runway or on the ground, and takeoff loads. You might have known about the takeoff loads, how they act, and moreover the inertial load. When an aircraft is changing the acceleration or it is moving fast or slow, a type of force which is generated in an aircraft is called as the inertial load and manual loads. These maneuvering loads occurs when aircraft turns or climb up or climb down or in some other deviated from the normal flight conditions. Okay, in order to understand about the inertial loads, let us consider an aircraft has a rigid body, and we model the rigid body as an arbitrary body of some arbitrary sections. This is an arbitrary section of a body which is shown, and you may observe that there is an axis x and y, and this arbitrary body has a mass of m, and r is connecting from, and we have a small elemental length or elemental volume of delta or mass. It is called as elemental mass of delta m, and this delta m is at a distance of delta r. Sorry, this delta m is at a distance of r from the origin and theta from the x axis, and this body is rotating at a constant angular velocity of omega. As a result, there is a centrifugal force which is acting on the rigid body, which is moving away from the body, called as omega square r delta m. Omega is the angular velocity of a body. This is a case when there is a uniform angular velocity, and this angular velocity can be resolved into the x and y component as omega square x delta m and omega square y delta m. Angular force F can be written as m omega square r, mass into distance into square of the angular velocity. And similarly, we have obtained this and we have resolved it along the x and along the y axis. Okay, the net resultant force is a integration or summation of omega square x dm. Since the angular velocity is constant, we can remove that from the integration symbol. What we get is that the force acting along the x direction on a rigid body is given as omega square integral x dm, and when you observe along the y, it is omega square integral y dm. And note that we have known the quantity integral x dm x dm is nothing but the centroid x bar into the mass times. And similarly, integral y dm can be written as y is a centroid into m. Okay, this is the case when the force is acting along the x and y direction on a rigid body when it is rotating with a constant velocity, angular velocity omega. And here we are not considering the translational velocity. And moreover, suppose now the rigid body is subjected to angular acceleration or deceleration alpha in addition to a constant angular velocity. Okay, when there is a sudden movement of an aircraft or when it is rolling or yawing or pitching. It executes a non-linear uniform angular velocities. As a result, if we consider as a uniform acceleration of alpha, what we can write is that the force acting on an aircraft is given as alpha r into delta m. Alpha is the angular acceleration of a rigid body and r is the radius vector for small elemental mass delta m to the origin. And you can see that this is a rigid body. Once again, this is a rigid body and this is the center of gravity, and the origin A is away from the center of gravity, and we have an angular velocity of omega, and we have uh, alpha, the angular acceleration alpha. Theta is the angle from x axis to the radius vector r, and the force acting, and you can see that this angle is 90 degrees. The force is acting along this direction, which is given as alpha r into delta m. Okay, now the net resultant force can be written as f of x is equal to integral alpha y dm, since alpha is constant, and what we write is that alpha is equal to integral, we are removing alpha from the integration symbol. Finally, what we get is alpha integral y dm. And the major concentration what you need to do is that on the axis on Fy, and the Fy is given as minus alpha integral x dm. You may observe that a negative sign in the Fy direction. What might be the reason for this? The thing is that when you look into the diagram, and this alpha x dm is acting in negative direction of the y axis, but alpha y dm, that the force of y is acting along the direction of x axis. This is the reason why f of y is negative and uh, fx is positive. Okay, now we go into the symmetric manual loads. In symmetric manual load, we consider the motion of an aircraft initiated by movement of control surface in the plane of symmetry. When you consider an aircraft from the top view, this is a top view of an aircraft. This is the top view, and this is the plane of symmetry. And these symmetric loads are applied when there is a movement of control surface of an airplane in plane of symmetry, and that happens when there is a deflection in ailerons, sorry, in elevators. As a result, the airplane will be pitching up or pitching down. During this time, the forces are acting on an airplane. This is called as the symmetric maneuver. Okay, and this symmetric maneuvers comes because of loops, straight pullouts, and bunts. Calculation involves determination of lift, drag, tailplane load at a given flight speed and airplane. And our main aim is to calculate the lift, drag, tailplane loads at a given flight speed and altitude. And moreover, the lift also depends upon the altitude. This is one of the most important parameter which we should not neglect. This is altitude. Okay, this is the case for a level flight. When you clearly look into the level flight diagram, we have a weight which is acting along the center of gravity, and the drag is acting along this direction. We have the most important thing which we need to discuss is that the lift force which is acting at the aerodynamic center, and the moment about the aerodynamic center is given as m naught. V is the velocity of flight, and in opposite direction and parallel to the velocity we have a drag force d. You can observe that. And P is the lift force generated on the tail plane. The lift force generated on the wing is given by L, and the lift force on the tail plane is given by the P. The distance from the center of gravity to the aerodynamic center of a tail plane is given by the length L, and the distance from center of gravity to the aerodynamic center of a wing is given by the length L. And T is the thrust force, that is the power or the thrust generated because of aircraft engine, and this alpha is an inclination of uh, airplane neutral axis to the velocity. And you can observe that. And another minor parameters which we have not discussed is that one is B and C. Here you can observe that B, the distance between the center of gravity and the length of the drag is given as B, and the distance between the thrust line and the center of gravity is given by C. Once you look into the diagram, you can clearly visualize what the parameters is, and this is the free body diagram of a flight when it is in level flight, that is no manual. Okay, now resolving the forces in horizontal and vertical direction. The first thing, we have identified the forces which is acting on an airplane, and the second thing, we have also identified the moments which are produced on an airplane, and the third thing, we have calculated the distance, or we have a distance from center of gravity to the other force lines like drag, thrust, and other things. Now the net force acting in horizontal direction. When you look into the diagram, what forces is that T and V acting in the same direction, and D is acting in the opposite direction. Sorry, in a horizontal direction. It was in a vertical direction. The lift force in vertical direction. Sorry, this is the vertical direction and this is the horizontal direction. There is a minor mistake here. In the vertical direction, what the forces we have is the lift force L, which is generated from the wing, and the lift force P, which is generated from the uh, tail plane. These are in same direction, and what we have is the weight which is acting towards down, and sum of the forces which is acting in vertical direction is given as L plus P minus W equal to 0. And similarly, the net forces which are acting in horizontal direction, this is vertical. Okay, T minus D. You can identify only two forces. One is T and D. And what we are doing is that we are neglecting this inclination alpha. In real flight condition, this inclination alpha is very less, and we can easily neglect it. And the most important thing, what we never forget, is that the moments produced uh, about on the aircraft. And when you can take the case of moments, you can look into L into A minus D into B minus TC minus M naught minus PL. Let us come into this equation. And what we know is that the moment M equal to R cross F. This is in vector form. And simply, what I can say that moment M can be written as the distance D into some force F. First, we need to identify the force, and then we need to identify the distance. Here, the distance is that distance from the force to the center of gravity. For example, when you take a body, when you apply a force along this direction, and if you need to calculate a moment force, this is the R. R and F should be perpendicular. This is most important thing. Let us clearly go into the free body diagram of flight. Okay, now nose down position is taken as positive and nose up position is taken as negative. And this is not a compulsory or thumb rule. We can also alter. We can take this nose down as negative and nose up as positive. But I'm taking this configuration. And you can see that. Let us identify the force which is in nose up position. M naught is the moment which is produced along the aerodynamic center of a wing. Plus, and from the lift, it is a nose up. So negative. And distance from the center of gravity to the lift is A. So that we got L into A is a positive one. So, let us take it is a positive and negative. That is the nose up is positive, nose down is negative, and nose up is positive. Okay, and lift into distance that is A. It is positive, that is LA. And next force what we have is the drag force, which is nose down position. And the distance between the drag and the center of gravity is B. And what we have is that the other dB. And now we concentrate on the thrust T. The distance between the thrust line and the center of gravity is C. Since it is a nose down position, we are taking it as negative and it is T into C. That is what we get. And M naught is a nose down position. That is the reason we have taken it as negative. And when you consider a tail plane, the load acting on a tail plane, it is a nose down position and we should take it as negative. And distance from the center of gravity to the force arm P, the force is L. And the moment produced by the force P is L. Finally, when we sum up this, what we get is L minus dB minus Tc minus m naught minus PL. This is the force which is that is a moment which is acting on an airplane. Okay, now let us simplify. Okay, let us assume the lift force which is generated by the tail plane is very much less than the wing. What we have is that, sorry, I think there is some mistake here. I'll write that here. The lift force L can be written as CLS into 1 by 2 rho V square. And rho is the density of air, S is the wingspan, and L is the lift. And it is approximately equal to the weight of an aircraft. This is a case when the force acting on a tail plane, that is the lift acting on a tail plane, is comparatively less when compared to the lift acting on a wing. And moreover, 90% of the lift force is generated by the wing itself. In most of the cases, the power P, T and D are small as compared to L and W. So what we can write is L equal to approximately equal to W and P equal to approximately equal to W A by L minus M naught by L. You can deduce it easily from these equations. Okay. Finally, symmetric maneuvers. When you draw this is the in previous what we have seen is that the free body diagram of a flight when it is in level flight condition. But when a flight is executing a pull up or pull down, in this case we are taking only the pull up maneuver. You can see that velocity which is a curved. And moreover, let us identify the force which is acting on a airplane which is in manual flight, that is the pull up. And we have a weight which is N times W. N is a load factor. N can be written as N equal to The load factor N is equal to the lift force into the weight W. Okay, and the weight NW is the force which is acting towards the downward direction, and it is N times W. It is not W. And lift L is acting along the aerodynamic center, and P is acting along the tail plane, and L and A are the distance from center of gravity to the tail plane lift and main lift. And finally, what we deduce from this equation is that resolving forces in vertical direction and horizontal direction, as well as uh, movements. Okay, when you look into the free body diagram of a flight, let us identify the forces which are acting in the horizontal direction. One is the drag D is acting along this direction, and moreover we have the uh, force FW, and moreover this FW and D are okay. This is drag D, and this is force FW, and the other force is acting, that is the thrust force, which is acting at an angle of alpha. This is thrust T acting in alpha direction. And finally, what we can write is this T cos alpha plus FW minus D equal to 0. Finally, what we get is the equation T cos alpha plus FW minus D equal to 0. Now, look into the forces which is acting in vertical direction. Okay. Okay. In vertical direction, we have a force NW, and we have a force L and force of P, and we have a force at an angle of this is the thrust T. Finally, what we can write is that L plus P plus T sine alpha minus NW equal to 0. Okay. L plus P plus T sine alpha minus LW equal to 0. And the next most important thing what we need to deduce is that the pitching moment along the aerodynamic center, or sorry, about the center of gravity. Let us identify the moments which is produced along the aerodynamic center. Okay, you can observe these equations. Since alpha is very small, this alpha is inclined along the direction of velocity. What we have is that in nose down we have positive, and nose up we have negative, and what we have is T into C positive, and nose up is minus L into A, and plus P into L, and we have an aerodynamic which is nose down position minus M naught, and drag something like D into D. I am not considering the sign. Finally, what we get is this equation. That is LA minus DB minus TC minus M naught minus LP. LA, that is the lift into distance arm. Since it is a nose up position, we have a positive direction of movement. And when you consider P, it is a nose down, we have negative P into L. And since M naught is in negative direction, we have uh, minus M naught. And the thing is that since the drag is a nose down position, what we have is D into B. Finally, we have discussed about the symmetric maneuvers and the force acting uh, on an aircraft in the different phases. Thank you very much. This is Varun Muruganti signing off.
Like, share and subscribe. Hit the bell icon for more updates.